All right, so week 5 here. So my plan for today is to talk about homework 3, which I just graded and sent you comments on last night. So I want to talk about homework 3, see if there's any questions on homework 4. I assume there's going to be questions on the interrupt stuff, but we'll be going over that also. See if there are any questions on Lab 3, talk a little bit about the midterm, and then start talking more about interrupts. So we started the subject of interrupts on Thursday. I want to go into that in full detail, tell you everything that you need to know to do Lab 4, and then start talking about Lab 4. And if we have time, we'll start talking about the next section, which is timers. I've decided not to put anything about interrupts on the midterm, by the way. Okay, so don't panic about that, but don't ignore it because, you know, it's going to be part of what we do the rest of the course. But everything that's on the midterm is stuff that we've already covered in previous lectures. So let me start off by talking about homework 3. So I graded that and sent it back to you, and it looked good. The programming part seemed really good. Access bit, about 2/3 of the people nailed it. The other third pretty much got it backwards, which is not bad because it means you probably just flipped the meaning of a 0 and a 1. But let's go through the homework. So question 10 was about the access bit. Okay, and there's a couple of things to keep straight here. The first is when we have the access bit, A, if it's equal to 0, that means we use what's called the access bank. If A equals 1, we use what's called the bank select register. Bank select register isn't something we've had to use, but it basically means 0 extend the operand. So remember, our instructions are something like, you know, clear file register 0x40 or clear file register 0xFF. If our access bit is 1, this operand will get extended with zeros to the left. So this would turn into 0x040. This would turn into x0x0FF. If A is equal to 0 and we're using the access bank, we sign extend the operand. So if we say clear hex 40, that gets sign extended. Well, the most significant bit of 40 hex is a 0, right? In binary, this looks like this. That's the bit that gets extended. So this will get extended to 0x040. But if we clear F hex FF, in binary, that looks like this. This most significant bit is a 1. So when we sign extend it, we tack 4 1s on the end. So this is the actual address hex FFF. Okay, so if you want to clear something that has a 0 in the leading bits, you can always just set the access bit to 1 and you're done. If you want to clear something that has 1s in those leading 4 bits, set the access bit to 0. But that only works if your operand has a most significant bit of 1. Alright, so what does that mean? For these first 2 cases, access bit doesn't matter. Third and fourth cases, you want to 0 extend, the access bit must be 1. Okay, that's your only working choice, to make the access bit 1. These 2 you want to sign extend, these 3 you want to sign extend, make the access bit 0, and then these 2 we want to 0 extend, make the access bit 1. And the possibly tricky thing is that when A is 1, we're 0 extending. When A is 0, we're potentially extending with a 1 because we're sign extending. So those feel backwards sometimes, but put it on your note sheet, and you should be fine. Question 32 I looked at, but I did not grade because there may have been some confusion about what I was asking. When I ask for the PC of an instruction, I'm asking for where that instruction is located in program memory. Okay, not the address that it's going to jump to or the address in memory that it's looking at, right? But what is its location in program memory? And I'll try to word it explicitly like that in the future. But the PC of each instruction means if you looked at the disassembly listing, what would be the address of each instruction? Okay, the origin statement has no address because it does not get stored in program memory. It's not an assembly language instruction. It's not going to compile or assemble into machine code. It's saying that the next instruction will get stored though at location 20. So increment F is stored at location 20 hex in the program memory. Call is at location 22. Why? Because increment takes 2 bytes and it started at 20. So increment was at 20 and 21. Call starts at 22 and it takes 4 bytes. So this is at 22, 3, 4, and 5, which means the branch will be at location 26. And then origin 40 says the next instruction will be at 40. This is not an instruction. That does not get assembled into ones and zeros. This is the next instruction, decrement something, that gets stored at location 40. Takes 2 bytes, so this is at 40 and 41. Return gets it stored at 42 and 43. End is not an instruction. It does not generate assembly machine language code, so it doesn't get stored in program memory. So it's 20 for the increment, 22, 26, 40, and 42. And then in 33 I say if you replace the branch begin with a go to begin, will it change anything in your answer? And in this case it doesn't. This is still going to be at location 26. But if there was an instruction after this, that would be stored at a different location. If we had another increment down here instead of an origin, if this is a branch is at 26, the next instruction would be at 28. If it's a go-to at 26, the next instruction would be 2A. Okay, 42 decimal. Because the go-to takes 4 bytes, the branch only takes 2. Does not have anything to do with how many cycles it takes to execute. It has to do with how much space it takes in program memory. And the thing we don't specify in assembly language is you know, we say start at location 20. Unless I say otherwise, just pack everything in as closely as you can, one instruction after the other. This takes locations 20 and 21. Go ahead and put this right at 22. Right, everything gets packed in one after another, unless we say something like origin, and I say, okay, well now jump down to location 40, put this at 40, put this in the next spot, and so on. All right, so that's good stuff to keep in mind. Conditional branching, so 34, I just wanted people to look at the status bit and make a sketch of it to make sure they had seen it, so that was fine. I didn't give or take away points for that. All right, conditional branching and conditional stuff. So I gave a lot of leeway in this, because we haven't gone over it a whole lot. We've done some of these, but let me give you some high-level things to keep in mind, and then let's go through some of these in detail. So when I give you questions like this, and I'll try to be explicit about this in the future too, I'm looking for a snippet of code. Okay, you're writing pick assembly language corresponding to this high-level code. You're not writing an entire program. Okay, which means you're not putting in an origin statement, you're not doing an include unless you need a symbol, you're not putting an end statement at the end. You're pretending that you're a compiler. Okay, we have 2 statements here. The first says x equals x minus 1, the second is an if statement. And what I want you to do is write some assembly language code that a compiler might produce to execute these 2 instructions. And what you can assume is that there's stuff before this, and there's probably stuff after this. There's a label somewhere called somewhere, right? There's a variable somewhere called x that has been defined somewhere previously in this program. So I'm not looking for you to write an entire program, I'm not looking for you to set up ADCON 1 or port A or anything like that. I'm not looking for you to loop. I'm looking for whatever assembly language will do these two things, and just that. Okay, set x equal to x minus 1, check to see if x is 0, and if it is, go to somewhere. Alright, so let's look at that one. X equals x minus 1, if x equals 0, go to somewhere. Go tos actually exist in C, by the way. People don't always say that, but it's a valid statement in C. He just raises eyebrows if you use it. But if you're a C compiler, you have to deal with go tos. Alright, so how would I write this up? Maybe I would put a comment in here saying, what am I doing right here? X equals x minus 1. Okay, that's optional, but you know, make things clear. Okay, how do we subtract 1 from x and store the result in x? That can just be as simple as decrement file register x. Alright, next thing is if x equals 0, go to somewhere. Well, there's a lot of ways to see if x is 0. So some people put a 0 into w, and then added w to x, and then did a branch of 0. That'll certainly work. Some people put a 0 into w, subtracted that from x, and did a branch of 0. That'll work. You could also do move f, x comma 0. Copy the contents of file register x into the w register, and then branch of 0. That'll work. You could also just say move file register x, move x into itself. It doesn't change anything except it will update the status register. If you look at the datasheet table 20-1 at the move f and you look at the status bits, you'll see a z in there. Move f x will copy x to itself, but it will update the 0 bit. And so you can say branch of 0. But it also turns out you don't have to do any of those things because decrement also updates the status register, including the z bit. So once I've decremented, my 0 bit reflects the following is the thing that I decremented x equal to 0. So right here I can just say branch of 0 somewhere. And that's my whole answer for question 35. It's half as long if you don't put in the comments. Now these other things are perfectly fine, and actually if you were an inexpensive compiler, you might not do this. You might compile this, change this into decrement fx, and then completely forget about it, and just say, okay, let's do if x is equal to 0. And so you would say something like move fx and then branch of 0. If you were an optimizing compiler, you would say, hey, I already know whether x is 0 because I did a decrement. So either way, lots of options there. All right. What happens when this runs? X gets decremented. If the resulting value of x is 0, the CPU will jump to a label, you know, somewhere, which we haven't specified, but presumably this label exists somewhere in the program. It'll start executing there. If it does not branch, it will go ahead and execute whatever instruction is at the next location in program memory. We don't know what it is, right? But we don't have to specify it. Go ahead and assume that this is just, you know, a couple of lines of code that you're assembling. So is everybody clear on that? Because you're going to see these kinds of questions on the midterm. And you'll make life easier for you, and it'll take less time if you keep these things in mind. Don't write an entire program. Just take these lines and write whatever assembly language you need to execute these instructions. So 36 says if x minus 1 equals 0, go to somewhere. All right, if x minus 1 equals 0, go to somewhere. So subtract 1 from x, and if it's equal to 0, go somewhere. Okay, if you wrote this in C, and you set x equal to 10, and you executed this statement, what value would you expect x to have after this statement is executed? Hopefully not. So if x is equal to 10, right, this is saying compare this value to that value. But it actually does not say set x equal to x minus 1. Okay? An if statement is saying, evaluate the left side, evaluate the right side, compare them. But when you're done, x should be unchanged. X should still be equal to 10. Okay, that's an important aspect of most programming languages. Because we're not trying to modify x, we're just trying to see something about it. I want to know if x was equal to 1, for example. So when you code this into assembly language, right, don't change the value of any other variables. And I mentioned this in Canvas when I posted the problem numbers to work on for all these problems. I said you can change the W register, because that's a scratch register. But don't change the values of any file registers unless you're asked to do that. If it says, increment Z, go ahead and increment Z. But if you're just looking at file registers to tell whether or not some condition is true, you should not change the values of any of those file registers. All right, does that make sense to everybody? Now here's an exception. If you use something like a pre-decrement, right? I don't know who answered that question a moment ago, but this does exactly what you said, right? X will actually get decremented, so x will be replaced with x minus 1, and then that will be compared to 0. So after this executes, if x started off at 10, you would expect x to be 9. Okay, but that's a special sort of feature of C. Like this, you don't actually want x to change. X should still be equal to whatever it was before. So how do you do this? Well, we want to know if x minus 1 is equal to 0, so we can subtract 1 from x. But let's put the result somewhere other than back into x. Now, if I don't say comma 0, the result just goes back into x, and x is changed. But I can put it into the W register, that's a scratch, or I could have a temporary defined somewhere and I could copy it into, well, I can't copy it into a temporary. I could copy X into a temporary and then decrement it, right? But the easiest thing on the pick is just throw it into W, and then you can say branch of 0 somewhere. Does that make sense? These are tricky until you get the hang of it. But once you start writing like this, it should start to click. All right, 37 is just like 35, except we don't do the decrement in the beginning. But since we didn't do the decrement, we don't have the 0 bit set, right? We need to somehow know if x is equal to 0. And so here's where we can use these different ways to see if x is 0. We could just say move file register x and branch of 0 somewhere. That's probably your easiest. It copies x to itself, but it updates that 0 bit. I could do a comma 0, but then I'm changing the value of the W register. And if I had some other thing that I was keeping in the W register, I would have to save it somewhere else. This kind of has the fewest side effects, right? All it's doing is updating status bits. So this would be a good solution, but some people added 0, subtracted 0, some people put it into W, and so on. There's lots of ways to do this. All right, if x equals 0, z equals z plus 1. All right, well, we got to check to see if x is equal to 0 first of all. So let's go ahead and move file register x. And then if it's equal to 0, we want to do our increment. Okay, we've got a lot of choices here. One choice would be, if it's equal to 0, go to somewhere temp. Where temp is going to be a label on some code that says set z equal to c plus 1. All right, move fx, so copy x to itself, update the 0 bit. If the 0 bit is set, jump down to temp, which will increment z. What happens if x was not 0? Is it going to take the branch?
No, but it will still increment z.
But it will still increment z, right? It won't take the branch, but it will therefore execute whatever instruction comes after this branch of 0. So if I write my code like this, right, it doesn't take the branch, it's going to fall through and increment z. But I can put something else here to happen if x was not equal to 0. For example, I could say branch to skip. Now if x is 0, it comes down to temp, increment z. If x is not 0, it does not branch, so it goes to skip. And where should I put skip? I gotta put it right after my increment. Okay, so check the flow of this. If x is 0, comes down to temp, increment z, ends up right here. So if x was 0, z got incremented. If x is not 0, it branches to skip, ends up right here, did not do the increment. Okay, it's a pretty direct mapping of that intent. Suppose I wanted to do this. If x is 0, z equals z plus 1, else z equals z minus 1. So test x. If it's equal to 0, come down to temp, which will increment z. If it's not equal to 0, it's going to skip the branch of 0. It's going to come down to whatever this next instruction is. So I'm going to make this decrement z. And I can't just leave it at that, because if I just write this after I decrement z, I'm going to increment z. After I decrement z, I'm going to say, let's go to skip. All right, test the flow. If x is 0, we'll branch to temp, we'll increment z, and we end up here. So that took care of that. If x is not 0, we will skip this branch, we'll decrement z, we'll branch to skip, we'll end up here, and we've done that. All right, is this making sense? And it's a little like physics in that there's no formula you can use. Well, there is, but there's no easy formula that says, okay, so if I have this, I need to have a branch of 0, and then I need to do a branch to skip, and I need to have a temp, right? You've got to construct this stuff yourself. It's a bit of a puzzle, right? But I guarantee the more you do this, the easier it gets. Right, and it's like, you know, programming in C. The first time you try to write an if statement or a for loop, it can be really confusing, right? After you've written enough of them, you look at a for statement and you know, oh, okay, that's what's going on. You don't have to think about it in terms of each little detail, right? What does this semicolon mean, and so on. It's the same thing with assembly language. It's just a different language. It's a lot lower level, and you're doing, you know, a lot of jumping around and skipping over things and so on. But it just takes practice, right? And the better you get at this, the better you are at programming, probably the better you are at engineering. Because it's problem solving, it's breaking problems down, it's keeping multiple pieces in your head and figuring out how to put them together in a different way. It's a really good skill. It's totally worth your time, you know, investing in working on problems like this. Okay, that's my sales pitch. So if x is equal to y, z equals z plus 1, well, almost no difference. Okay, if we want to know if x is equal to y, we do a subtraction. So let's put, say, x into the W register, and then subtract the W register from y, and again put the result back into W. Because if x equals 5 and y equals 5, and I execute this if statement, when I'm done, I expect x and y to both still be equal to 5. Right? There's nothing in here which says, oh, and set y equal to 0 while you're at it. Right? But if I don't put this comma 0 at the end here, I'll put x into the W register, I'll subtract x from y, and I'll write the result back in y. This is going to change y to 0. And the programmer who's writing this code is going to get all tripped up because they said y equal to 5, they checked this condition, and suddenly y is equal to 0. All right? So make good use of the W register or some other temporary location so that you don't change the values of things that aren't supposed to change. So the status register is updated, and if x was equal to y, then x minus y is equal to 0. So we can say branch if not 0, skip, and then down here we can say increment file register z, and we can put skip down here. Or we could have said branch if 0, go, otherwise branch to skip, and then at go we could have said increment file register z, and then this could be skip. So we do x minus y. If it's equal to 0, we come down here, increment z, and we end up at this statement. If x is not equal to y, we don't take the branch, so we do the branch to skip, and we end up down here without incrementing z. And if you want to do if x is not equal to y, it's just going to change the sense of your branches. Instead of branching if not 0, I'll branch if 0. Right? Because if x is not equal to y, then x minus y will not be 0. So if it is 0, I'm going to skip. Otherwise, I'll do my increment. So if x is equal to y, z equals z plus 2, else z equals 0. So let's put x into the W register, subtract that from y, put that in the W register. Branch of 0, I'm going to call my label instead of temp or skip, I'm going to call it something more meaningful like equal. Okay, equal is the label that I'm going to branch to if x was equal to y. Otherwise, if I don't take that branch, it means x is not equal to y. Well, I'm going to put a comment here which says x is not equal to y. So that I know when I'm writing this code and debugging it, if I get down to this spot in my code, right, it means that x was not equal to y. Well, what do I want to do if x is not equal to y? I want to clear file register z, and then I want to go to, I'm just going to say done, where I'm done with this if statement. Alright, so I've handled the else. If x is equal to y, it will branch down to equal. Otherwise, it'll fall through, clear z, and go to done. So what does my equal code have to do? This is a label, but I'm going to put a comment on here saying x is equal to y. Well, I want to set z equal to z plus 2. So I'll put a 2 into w, add w to z, and put the result back in z, right? And this is a case where I am supposed to modify the value of z. So now z is equal to z plus 2. And I'm done, so I'm just going to put my done label down here. And that's a good rendering of that statement. Yeah, you can also move a 0 to z up here instead of clearing it. So this is why we program in C or Java or Python or these other languages, because this is one statement. This is 1, 2, 3, 4, 5, 6 assembly language statements and a couple of labels. And if you are stumbling around in the dark and you come across this, it's like, what the heck is that, right? But if you walk down the street and you see this written on a wall, you know exactly what it's saying, right? If x and y are equal, let's add 2 to z, otherwise clear z, right? So we prefer to write like this, but the PIC processor or other processors understand things at this level, right? So a compiler translates this into this, and then an assembler turns this into the ones and zeros, because each of these instructions goes directly into ones and zeros. That's just, a homework problem, filling in the templates. But again, if you're able to take this and translate it into this, then you're working the essence of programming, right? You're breaking these big things down into smaller things, and that's a really valuable skill. All right, and again, for all these questions, we're assuming there's stuff before this and there's stuff after this. So I wouldn't want to, put a label at the top and jump back up to there when I get to the end, because that's an if inside an infinite while loop, right? Which is a different beast altogether. Now, when we write code for our labs, we've said at the bottom we always want to branch back up to the top. Well, that's not always going to be true, but so far it's been true. Why? Because we're writing entire programs. And if we wrote this and loaded it into a PIC processor and that was our whole program, there's no telling what's going to happen after this statement. Whatever happens to be in program memory is going to get executed, right? Memory's not empty. Just because we haven't written any instructions here doesn't mean there's not some instructions in the program memory. So if we're writing a whole program, we need to do something, and typically what we can do is we can go back up to the top, if that makes sense. But when you're just writing a set of assembly language instructions to correspond to some behavior that you want, right? Don't throw in extra loops, things like that. Don't initialize your variables. Don't load a value into x in the beginning. Don't load a value into z in the beginning, right? Just assume you're just writing this piece of code and there's already stuff before and there's going to be stuff after. All right, questions about that? Because that's definitely going to be part of your midterm, is things like those problems. Alright, silence is always worrisome to me, but I will have faith. Alright, we talked about 43 through 48 last time, and I did not grade those, okay, but we talked through them. Any other questions on homework 3?
Could we go over through that?
Go over which?
Number 10.
We already went over that. The access bits?
Yeah, he got a little late.
Oh, it should be on the recording.
Okay, alright, then I'll watch it.
Alright. Other questions? Alright, questions on homework 4. And like I said, I know we haven't gone over most of what you need for the interrupts. Alright, can we go over the last pop on number 49? So number 49, we push a 10, we push a 20, we pop, we push a 10, we pop, pop, pop. Alright, so let's work this out. So a couple of pushes, a pop, a push, and then 3 more pops. So let's draw our abstract stack. And our top of stack is pointing to the beginning. So when we push a 10, that goes right there, top of stack goes here. Let me call it stack pointer. Top of stack is usually the contents of what's on the top of the stack. Stack pointer is pointing to the next thing that you're going to push. So stack pointer moves down to here. When you push 20, stack pointer will get put in there, and 20 gets put there, stack pointer moves down to here. So let me do this the way that I would like to see it written on your homework. And I think I asked you for a top of stack, and no, it was just an abstract stack. Alright, so here's your stack pointer. Okay, you say push 10. So 10 goes there, stack pointer moves down 1 spot. You say push 20. Well, the 10 is still in there, the 20 gets written where the stack pointer is, and the stack pointer moves down another spot. You say pop, and all that a pop does is decrement the stack pointer. So I'm using empty boxes to represent not an empty memory location, but really a question mark. Right, to really say we have no idea what's in here, but you can just leave them empty if you want. But the important thing to notice is that when I pop, that 20 is still in the stack. It doesn't disappear, it doesn't get replaced with a random value. Some architectures will. Alright, so now we do another pop. And we've still got a 10, we've got a 20, but the stack pointer is now pointing to that first location. That means our stack is empty. So if we do one more pop, it depends on the architecture, but this is what we call a stack underflow. Because we tried to remove something from the stack, but the stack was already empty. So if you were making a picture like this for yourself, you might note stack is empty here, stack is empty here. Anytime the stack is empty and you try to do a pop, you're going to get a stack underflow. And it's possible the stack pointer will simply stay at 0. It's possible it will change to some magic value to indicate there was an error. For example, on the PIC processor, it'll set bit 6, I believe, to a 1 to indicate that a stack underflow occurred. But this is an abstract stack, so you can just note that you got an underflow.
Would that only be an underflow if the stack was empty to start with?
Yes, correct. If there was already stuff on the stack, then we would have popped off whatever was at the top of the stack at that point. Thank you.
Okay.
All right, cool. Other questions? All right, lab 3 questions. How was lab 3?
It was a bit.
Did it work?
Well, it was a bit long. I got it to work, but I felt rather fatigued at the end.
Okay. It's the first time we've used that lab in Engineering 270. Because normally at this point in the course you're working with these little PIC processor controlled cars and driving them around in circles and lines and avoiding obstacles and things like that, and we couldn't do that online, so Izad and I decided to do a traffic light lab, so we'll see how it went.
I thought it was cool, considering the fact that we built the traffic light originally from various separate chipsets.
Mm-hmm.
Just bit, one traffic light into one single chip.
Right.
Which I thought was pretty interesting.
Yeah, it's a good argument for using a microprocessor instead of a bunch of chips, right? And it's certainly easier to correct mistakes than trying to find a wiring error. I coded this up myself last week, and I was surprised it ended up being well over 100 lines of code, which was more than I expected. So we'll see how it went, but I'll be somewhat gentle in grading.
Yeah, someone found bit-specific arguments that you could put in that I found were extremely helpful.
Like bit set and bit clear and bit test.
Yeah, and bit toggle.
Yeah, those are cool. Yeah, we have 3 bit instructions: bit set file, bit clear file, and bit toggle file, that let you name a particular bit number in a file register and either set it to 1, 0 or complement it. We'll use those a lot when we deal with interrupts too, because interrupts, we're mostly dealing with individual bits inside larger registers. And instead of trying to figure out the whole 8-bit bit pattern and then moving that in all at once, we can use these bit set, bit clear instructions. Alright, well let me talk about, for number 51, what would be the value of TOS, since we are given his instructions. 51, top of stack. So assume that the top of the stack, assume the stack starts off empty. So the stack pointer is 0. And we don't know what top of the stack is in the beginning, so you just put a question mark for that. And for the stack itself, we don't know what's in any of the locations, but as soon as you say call, something will get pushed onto the stack, and then we'll know what top of stack is. Alright, so let me talk a little about the midterm. Midterm will be on Thursday. It will be done on Canvas. It'll be done during class time. It's going to start right at 12, okay, because I want to be able to lecture after the exam's over. So exam will start promptly at 12. It will be a quiz on Canvas that will open at 12, and you'll have 50 minutes to work on it. I will be in the Zoom meeting during the exam, so you can contact me through Zoom the regular way, right? Catch me in a chat window if you have any questions and so on. If anything bad happens, worst case, send me an email, right? And we'll figure it out. But I think everybody's got Zoom figured out at this point. I think everyone's got good connectivity, so hopefully there's no glitches in this. The exam will be 5 or 6 questions, I don't remember. And you will basically be, it'll look like a series of essay questions, okay? And you'll be typing code in or typing in short answers to questions or things like that. And it'll show as a series of essay questions. So it'll just give you the question, and there'll be a space for you to type in your answer, which will generally be a set of code or ones and zeros or whatever. I strongly suggest that instead of typing in, 30 lines of code directly into Canvas, type it into whatever your favorite editor is, right? And then paste it into Canvas, right? Canvas, like all things web, have a tendency sometimes to do something unexpected at the worst possible time. You hit the escape key and it closes out your window or goes back to a previous page or something. So don't put, your only copy of your answers directly into Canvas. I recommend putting them into an editor. It can be Notepad, it can be VI, whatever, right? And then just copy and paste. And if you've had me in any other classes, and I'm guessing your other teachers have probably done this, spend a little bit of time ahead of time figuring out how to copy and paste into Canvas quizzes, okay? It's not that hard, but sometimes it throws 4 spaces in between each line. Sometimes everything gets left justified. I'll work with what you have, right? But don't throw yourself into a panic during a 50-minute exam because you don't know how to copy your code and paste it, right? Because Canvas is doing something weird. So I'll open a practice quiz if people want to try that. And it'll basically be like homework questions. It'll be like things you've done in the labs. Okay, that's pretty much the bulk of it. It will not include interrupts, but everything up through and including interrupts is fair game. Okay, it won't include stacks either. But everything on the first 3 homeworks, everything you've done in the labs, everything we've talked about. It will spell this out in the quiz on Canvas, but my expectation is that you can use your own notes, okay? And you can use the pick data sheet, and that's it, okay? I don't want you using your old homeworks. I don't want you using your old labs. I definitely do not want you using MPLab, okay? So do not fire up MPLab and type code in there to check it out, and so on and so forth. And obviously, don't talk to other people. Don't go online and make queries in Google and things like that. So it's a regular exam condition. It just happens to be that we're each in our own location, but on our system, right? And just for the record, right, once you turn in your quiz, it will show up as a grade of 0 because I have to grade these things. So you won't get a 0. All right, any questions, concerns, worries about the midterm?
What is the time limit again on the midterm?
12 o'clock to 12:50, so it's 50 minutes. And it'll be set up on Canvas, so Canvas will close it at 12:50. If you've got part of an answer type in when it closes, I don't know what it does. Okay, so I usually set it up to close about 12:52, but treat 12:50 as the deadline, right? Get everything submitted by then. And I think it gives you a countdown or something also. And then we'll do like a 5-minute break after that, and then we'll go ahead and have a lecture for the second half where we'll talk about timers in detail, and go over the next set of homework. All right, other questions? All right, so let's take a 5-minute break. We'll come back, we'll start talking more about interrupts. We'll go through this batch of homework questions on interrupts, and we'll talk about Lab 4. Sound good? All right, I'll see you in about 5 minutes.